Stanford University.
So about 25 years ago, I got seriously interested in the question of why did these new graduate students coming into my physics research lab, how could they have done so well for so many years in physics courses and not be able to do physics? And that led me to first learn about and then participate in really a new way of thinking about science, teaching, and learning. And this is really the idea of approaching it like a science, and so that we do controlled experiments looking at different ways of teaching and measuring the learning that's produced between them, and figuring out then what works and why based on data, where we're judging what works on how much students are actually learning. Now, this is an area of research primarily carried out in undergraduate science courses. It was started in physics 30 or 40 years ago and is now spread across all the sciences, and we see quite similar results across them. And one of the things we found is the most revealing measure of learning are to look at situations where a simple relevant context to the topic you're trying to teach, and look at what scientists can do when posed with this question, what predictions they make and why. And then you ask students to do the same thing. And you compare the responses. Clearly, you often see big differences. But this is really the measure of what I'd argue is sort of flexible, useful knowledge, how well you can apply it in relevant situations. And we get very different results when we compare that measures with what people see from the usual course exams, which appear to be primarily testing if students have memorized certain facts and procedures that aren't good for too much beyond passing their physics course. So using these measures of learning, we then go out and like I say, do compared experiments. And since most classes are being taught with lectures, we compare those where the students are spending their time listening, the instructors are mostly telling them things, with various kinds of what I'd call sort of scientific teaching, where as we've evolved over time, different ways the students are practicing and doing activities, and the instructors are coaching. And we're not just comparing with lectures like this, we're comparing with ones with very charismatic, engaging lectures. Surprisingly, it does not matter very much in the results. And there's many, many results now published on this, and I'm going to give you a few my favorite examples. So in this is one study I was involved with, and it was looking at directly the amount of learning really produced in the classroom. And so we had two big sections of introductory physics where we carefully measured. They were very nearly identical in all respects. The two instructors were covering the same set of learning objectives in exactly the same amount of class time, a week of lectures. And then right at the end of that, both sections were given the same test that covered those objectives. And the comparison here was the first class was taught by someone who was a very experienced teacher of this material, had good student evaluations, ratings, and so by the current university standards of this and any other university would be considered a good teacher. And the other section was taught by someone who was a fresh PhD in physics, but had been trained in the program I ran and these methods and practices of scientific teaching. And so how did they do on the common test at the end? Well, you can see here, this is plotting the number of students versus their test score. Random guessing would give you 3. And you can see a profound difference in the distribution between these two classes. And really, the entire distribution in the class has moved up. And with, of course, the experienced traditional lecturer being much far below. Now that was just learning in the classroom. Here's an example which is looking at an entire course and also not comparing two different instructors, but comparing the same instructors, just they're using different teaching methods. And so this is work done at Cal Poly. They looked at the concepts of force and motion covered in this course and how well students could apply these to simple situations like a physicist would. There's a careful, good test for this. You use pre and post measures of how much learning gain the students get from class. They collected data for many years as these instructors were using traditional instruction, and they were getting gains of about 0.3. We have lots of data from physics. That's pretty good for a good lecture instruction. And then all the instructors switched over to this scientific teaching approach, and basically everyone jumped way up. You can see up here, they're now fairly consistent with much better learning, about a factor of 2 on average. Now, the thing I want to emphasize, these are the same people, the same instructors. The only thing they changed were the teaching methods they used, and you get greatly improved learning as a result. And just how great this is, I mean, most of them are about a factor 2. This person, their students are learning 6 times more than they were before they changed to these scientific methods. Finally, this is not looking at learning, this is looking at failure rates. This is work done in computer science by Beth Simon, who worked with me for a while, went back to UCSD and got the instructors there to change their teaching approaches for these core computer science courses. And as a result, after they changed over, the failure rates dropped dramatically across all of these courses. And so, again, we have the same instructors just using new teaching methods and getting much greater student success, about 1/3 the failure rates they had before. So you probably are wondering at this point, what's actually happening in these classes. And I know I don't have time to go into detail, but basically, instead of sitting listening, students are doing tasks. And so, for example, a physics class on electricity would start out with this question for all the students, this circle with batteries and light bulbs here, and closing this switch, what's happened to the brightness of that bulb? The students are given the task of answering individually, and then they have to discuss with their neighbors in the class and come up with the answer and the reasons behind it. And meanwhile, the instructor, like this one, is circulating around. They're listening in on those conversations, maybe briefly intervening, and most importantly, they're then, at the end of this question, leading a follow-up discussion where they explore the students' different reasoning processes and give them guidance as to how to go forward. And switching topics slightly, one of the areas I've been working in is how we can use technology to support this kind of learning by students. And so in this particular class, we wouldn't just give them the answer. They'd have to build this circuit themselves using this interactive simulations, and they would hook this up. They see what the cartoon electrons are doing. They close the switch, and they see what happens to the electrons and the light bulbs. And this really allows them to do further on their own exploration and testing and so on. And this is a project developing these simulations, something I started a number of years ago, and I guess they're going to be used about 100 million times this year, so it's getting to be a fairly big deal. One of the things I'm really interested in as a researcher is that these simulations let us explore a different area of teaching and learning than what people have been able to look at with other educational approaches. Namely, we can have how people go and discover things, how they figure out things they don't know, which they can do in a simulation, and it's very hard to test that otherwise. And so really looking at their strategies for discovery, and our goal is really to have people develop better investigation processes. just to give you an idea of how one can use these kind of things in a real course, this is just an example of the class I'm teaching now, a sophomore level quantum physics course. And there, the students, I give them this interactive simulation of a laser. And how a laser works is a very complex process with a lot of quantum physics in it. And these students are told to figure it out. And they can't do it at first, but after about 20 minutes working together in class with a little coaching, they're successful in really understanding in quite a lot of detail how a laser works. And this is only made possible by this technology. Usually students really can't learn ideas of lasers until they get much more advanced in their academic career. And of course, everybody should know about how lasers work, right? So if I sort of step back, all of this research combined, it's sort of demonstrating a fairly fundamental principle, which is that the effective learning of science, it really requires the person to be practicing the desired thinking processes and getting guiding feedback on them as they do that. Now, and that means one of the key elements is having carefully designed tasks that get them to practice that you can use in classrooms. And a lot of what the ongoing research in this field now has moved to is really thinking about what is the best designed task for particular subjects in particular areas, and what's the most effective feedback that you can give to have students learn the most effectively and efficiently, and how does this depend on students' individual characteristics. And then, as I mentioned, we're also looking at ways we can have technology to support this particular learning process. Now, a lot of people are wondering, well, how broadly does this apply? I think I can say with quite a bit of confidence that I'm pretty certain the same basic approach applies to other subjects and other levels. We just don't have data where people have actually done the comparative experiments there to say. We do have some data from K-12. It turns out there's a number of complications in both the implementation and actually carrying out the research on the effectiveness there. So we don't have nearly as clean and nice a data as we have from undergraduate classrooms. But what we have says, yeah, the basic ideas will still work the same. So from one perspective, the idea this is a better way more effective way to teach is it's really obvious. If you want somebody to learn how to play basketball, you don't have them sit every day in front of a blackboard and get told how to play basketball. You have to break it down into particular skills and practice those skills and get feedback on them. And from another perspective, it's completely consistent and supported by a lot of cognitive science research about how people learn to think more like experts and scientific reasoning, and it connects up well with the kind of work that Bruce was talking about and the kind of work that Carol talks about when you get into the details of what the people have to do to learn. All of these things show up in very consistent fashion. But from another perspective, this is a shocking and unbelievable result, and that is, universities like this one and everywhere else are filled with, faculty giving lectures on students telling them about science, and they're really sure the students must be learning from these, and they can't imagine any other way to teach it. And if we didn't have faculty like this, we wouldn't have been able to do that experiment like I showed you at the beginning, where, anyway, in summary, this kind of scientific approach of carefully measuring things and learning and teaching, it's giving dramatic results, and it's giving us important new insights and ways we can dramatically improve learning. But at the same time, it's a little slow to move from the research into the college classroom. And to finish with a medical analogy, it's what we really have is a lot of science faculty are really using the pedagogical equivalent to bloodletting when they've got, well-tested penicillin sitting on the shelf. So we have a ways to go, but we will get there. You just kind of have to remember that if you're trying to change a 1,000-year-old tradition, it does take time, even if you have science on your side. So thank you.
For more, please visit us at stanford.edu.